energy diagrams are a really fascinating and exciting way to discover what's really going on in the sciences. Now, if we look at this, this is a picture of Compton on the front page of Time. Now, it's not very often a physicist makes the front of Time magazine. Basically, he came up with the theory that photons have momentum. But remember, momentum is mass times velocity. And mass times velocity. Photons have no mass. So how does this work? Basically, let's go back to our atomic structure. You have in the center of any atom is your nucleus. And in your nucleus is protons and neutrons. And then you have electrons swarming around on the outside. But it turns out the electrons are at different energy levels. They're in different orbits. You remember this from chemistry. Let's think about this. Imagine you're climbing a ladder. Now, when you're standing on the ground, you're at your lowest level. You're at your lowest energy level, so that's called that n equals 1. When you go up a rung, you are increasing your energy level. Now, it's taking energy to go up the ladder. All right, and you can go up one rung at a time, or if you have really long legs, you can go up, you can jump two rungs at a time, correct? Or if you have really, really long legs, you can do the whole thing all at one time. But the point is, you are not the Wicked Witch of the West. You cannot hover between energy levels. So you must be on an energy level. Okay, you can't be between. This is a quantization of the energy levels. So as you increase energy levels, you're taking energy to get there. Now, in class, I will stand, and what happens if I were to fall? Well, I always joke that I will emit a photon, all right, basically, and hopefully it won't be a 4-letter photon. It'll just be a photon. So it takes energy to go up, but then when you go down, you emit energy. So you absorb going up, you emit going down. Now, that's what these quantum leaps are. I love the movie Quantum Leap. Suppose we start at energy level 1 and we go up. All right, a photon will be emitted if I go, say, from energy level 2 down to energy level 1. I'm going to get a photon. And if I get a photon, what do I see? I see light. All right? So, remember, my energy is equal to hf. So the energy of my photon that is going to be emitted is equal to hf. While if I'm going from a lower level to a higher, I'm going to absorb energy equal to hf. So it doesn't matter whether I'm being emitted or absorbed. The energy emitted or absorbed is always hf, where f is the frequency of the light. So this is the color. We're going to see different colors based on what is being emitted. Now, suppose, let's do the stairway analogy. Again, you cannot climb stairs and hover between. So at n equals 1, all right, we're at a certain energy level, and then we go up to n equals 2, n equals 3. If I were a ball, I can only go up to distinct levels. Now, what formulas are we going to use? The change in energy is hf, but remember, c is f lambda, so I'm going to solve this for f. F is c over lambda. So if I take this and plug it in here, you can't see that, h is c over lambda. E is hc over lambda, or hc over lambda. All right, so these are just two different ways of writing the same equation. So the energy emitted, I can tell you either the wavelength or the frequency. We know h and we know c. So I may ask for the frequency, I may ask for the wavelength. Now the Bohr atom is not correct, but that's okay. It gives us a very close approximation to what we need. This is an energy diagram. for a Bohr atom. And basically what's going to happen whenever I give you an energy diagram, I'm going to tell you the different energy levels. And do you see how to go from 1 to 2, the distance is greater than from 2 to 3, than from 3 to 4. This is common because the further out you go, it's a 1/r squared relationship, the energy goes down very quickly. So if we go from 1 to 2, we're absorbing. If I go from 2 to 3, I'm absorbing. If I go from 3 to 4, I'm absorbing. What are other ways I can absorb? I can go from 1 to 3 or straight from 1 to 4. Is that all of them? No, I can also go from 2 to 4. So there are a bunch of different emission spectrums I can see off of this. And of course, absorbing is going up, emitting is going down. Suppose I want to find all of the possible wavelengths of emitted light. And I've given you this diagram right here. Well, to go from ground to the next level is 1 eV. To go from ground up is 2 EVs. So let's see, this is let me go and label them. N equal 1, N equal 2, N equal 3. To go from 1 to 2 is 1 EV. To go from 1 to 3 is 2 EVs. So to go from 2 to 3 is 2 EVs. Now, if I ask for the wavelengths, apparently I can't spell wavelength, how do you do this? Well, E is HF, which is HC over lambda. So solve this for lambda. Lambda is HC over the change in energy. So this is HC, and we have to get it out of EVs and into joules, and I just did this all at once. So I get 4.14 times 10 to the negative 7 meters, or 4.14 nanometers. When I do it for the second energy level for 2 EVs, first one I did was 3 EVs, so this is going from 3 down to ground. The next one is going from 3 down to 2, gives me 621 nanometers, and then going from n equals 2 to n equals 1 gives me 1,243 nanometers. These are different colors. I will see violet, orange, and then I won't see anything else. It's all, the last one is infrared. Now you don't have to know that orange is between 590 and 630 nanometers. You'll have a chart. But this is exactly how you do these problems. HC, and you know what? You can go on and multiply this out. As a matter of fact, in my AP class, they actually have this on the chart as they've gone on and multiplied out 6.63 times 10 to the negative 34 times 3 times 10 to the 8th, and it's 1.9089 times 10 to the negative 25. So you can go on and do this. As a matter of fact, for this problem right here, you could go on and divide by the 1.6 times 10 to the negative 19. Oops, didn't do that right. 1.989 times 10 to the negative 25 divided by 1.6 times 10 to the negative 19 is error. I'm just having trouble with this. Okay. 1.989. Now I'm determined, folks. Times 10 to the negative 34 times 3 times 10 to the 8th divided by 1.6 times 10 to the negative 19 gives me 3.73. I could have done all this, where this whole thing is, let's see, HC over this 1.6 times 10 to the negative 19 is 3.73 times 10 to the negative 7. And then just divide it by 321. That can't be correct, can it? 6.63 times 10 to the negative 34 times 3 times 10 to the 8th divided by 1.6 times 10 to the negative 19 has got to be, teachers make mistakes all the time. And apparently I can't stick numbers in a calculator. All right. It's 1.24 times 10 to the negative 6. 6. Had to be that number right there, didn't it? Now, spectroscopy, can't say it, is the science of using these changes in energy levels to determine what an element is. Each of these are different elements. And because as they change energy levels, they give off different frequencies, they give off different colors, we can determine the different, what the elements are based on the colors they burn. We often get what's called emission lines. So mercury will always have an emission line that looks like this. Calcium will always have an emission line that looks like this, while sodium always gives us this bright yellow line right here. Different elements give us different emission lines, and all of this is based on our energy diagrams.